Okay, good morning. That was good. That was very good. Okay, so I pulled out the course calendar here just to let everyone see what's going on. Today we're going to look at 12.3, what's called the dot product. And then next Monday we'll look at the cross product. And then we'll finish the vector part on Monday. So notice that starting next Wednesday, we'll be looking at Chapter 6. We'll be doing integration again. Okay, so it's a good time if you want to go back and review a little bit of integration to prepare for next week. All right, just so you know what's going on here. Okay, my screen is back. So today we're going to look at 12.3. The dot product. So let's say we got two vectors, vector A (1, 2, 3), and a vector B 4, 5, 6. The dot product works this way. If you take a vector A and you dot it with another vector, so that dot, if these are numbers, then that just means multiplying them together. But they are vectors, right? Each one has 3 components or more or fewer, but they're vectors. When you dot two vectors, here's what you do. You take the first two numbers, the first component of each one, multiply them together, 1 times 4. And then you do the same with the second component, multiply together, and then add it to the third component, multiply together. So 1 times 4, that's the first. 2 times 5, the second. 3 times 6, the third. When you multiply this together, we get a 32. And note that if you dot two vectors together, you end up getting a scalar, a number. If you ever dot two vectors and you get another vector out of it, then you did something wrong. You should get a number back out of it, never a vector. So that's called a dot product. And in general, if A is equal to, let's say, A1, A2, A3, and B is equal to B1, B2, and B3. And when you dot them together, again, you multiply the components, line them up, and multiply them together. A1, B1, add them to A2, B2, and then add to A3, B3. Okay? Notice that this is also equal to B dot A, right? Because when you multiply two numbers together, it doesn't matter whether it's 2 times 3 or 3 times 2. You get the same thing. So A dot B and B dot A are exactly the same thing. The order is irrelevant. And one more thing to note. If if you take a vector and you dot it with itself, so let's look at this one right here, A1, A2, A3. If I dot this with another A, then I get A1 squared plus A2 squared plus A3 squared, right? And we can look at it as the square root of A1 squared plus A2 squared plus A3 squared, and then square together. And what's this thing over here? What's the square root of A1 squared plus A2 squared plus A3? The magnitude, yeah, very good. It's the magnitude of A, and then squared, right? So if you ever dot a vector with itself, then you will get the magnitude of the vector, but squared. Any question on the basic of dot product? Now let's look at what the geometric significance of the dot product is. Let's say you got two vectors. So here's A, here's B. And the angle between them, we'll call that theta. It turns out that if you dot them together, if you do A dot B, what you also get out is the magnitude of A times the magnitude of B times the cosine of that angle. So this is a very important formula to remember. So that number we just calculated on the previous slide, that 32, that's related to the magnitude of A and B and the angle between them. Okay? So let's find out what the angle is between the two vectors we had earlier, the A and B. We'll bring them back and do an example. From earlier, we knew that if you dot product of A and B here, we get a 32 out of it. Okay? And the magnitude of A turns out to be 1 plus 4 plus 9, so that's 14 under a radical. And the magnitude of B is 16 plus 25 plus 36 under a radical, and that's 77. Now I can use this formula in the red box. 32 is equal to radical 14, radical 77, cosine of theta. This is something obviously we have to use a calculator to calculate. get 32 over radical 1078. And theta is the inverse cosine of that number. And now we have to use a calculator for this last part to get an approximation. It's roughly 13 degrees. Okay, make sense? Yep. All right. Now let's take the angle formula a little bit further and find out a little bit more about what the number A dot B tells us. If you have two vectors, A and B, and they're perpendicular to each other, then what's the angle between, what's theta? Pi over 2, and what's cosine of the pi over 2? Cosine of pi over 2? 0, yes. Now that's something you have to know without a calculator, okay? Oops. Cosine of pi over 2, and that's a 0. Okay? So that means if you take the dot product of two vectors, then what that tells you is that the vector A and B are perpendicular to each other. Okay, guys, we need to switch the screen here because the recording is recording the other screen. So that means if you watch the video, it doesn't work so well. So I'm going to be working on this screen here. So it'll appear, you'll make it work, right? Actually, let's finish the thought here. And therefore, if two vectors are parallel, then theta, the angle between them, if you look at two parallel vectors, it could be like that, parallel to each other but pointing in the opposite direction. And the angle between them is pi, right? Or you can have A and B just lying right on top of each other. And therefore, the angle between them is 0. So when you get two parallel vectors, you get 0 for theta or pi. And therefore, A dot B is equal to 1 or minus 1. Excellent. Cosine of 0 is 1. Cosine of pi is minus 1. Okay, so that's if A and B are parallel. That means they have the same direction or they have the exact opposite direction. Make sense? Any question on this stuff? Good? Okay. Now, in many applications, if you have a vector just sticking out in space, so here's my x, y, z. And here's some vector. We'll use 1, 2, 3 again as an example. In many applications, what you want to do is to find out what is the angle between that vector and the x, y, or z axis. Let's call the angle between A and X. We'll call that alpha. So alpha is angle between A and x-axis. And the angle between y-axis and A, we'll call that beta. And finally, the angle between the z-axis and the vector A, we'll call that gamma. Angle between A and the z-axis. So for example, this could be, let's say, a telescope on Earth. Right now it's looking at something, but you wanted to look at another specific object that happened to coincide with the x-axis, for example. Then you need to know, you need to command the rotor, the motor in the telescope to rotate that amount to point at the direction that you want it to go. So in that case, we really need to know what is this angle alpha. And then we can figure out the angle we need to turn, so we are looking at the object we want to see. Okay, let's find out alpha here. So what we're going to do here is to use this formula again. A dot B is equal to magnitude of A, magnitude of B, cosine theta. So we're going to say that a new vector B is sitting right on the x-axis. In fact, I'm going to make it simple and make it a unit vector in the x-axis, the I vector. So that's 1, 0, 0. You could use any vector that sits on the x-axis, but we're going to be calculating the magnitude in a little bit. If we make a unit vector, the magnitude is 1, and that's very convenient. So we'll let B be the unit vector I, 1, 0, 0. In this case, that theta we eventually calculate will be alpha, right? All right, so let's find out what we need to do. A dot B, so where's my A? Here's A. A dot B, we get 1, right? Magnitude of A, we calculated this earlier, radical 14. Magnitude of B, it's a unit vector. Length is exactly 1. And that angle, we'll just put alpha in there now. So cosine of alpha is 1 over radical 14. And with a calculator, this turns out to be about 74.5 degrees. Okay? To find beta, we use the same trick. We find a new vector, b, that sits on the y-axis. And for convenience, we use the j vector. The magnitude is 1. Use the same formula again, a dot b. What would a dot b be in this time? 2, right, because 1 dot 0 is a 0, 2 dot 1 is 2, 0 times 3 is 0. So we just get a 2. Magnitude of A is radical 14. Magnitude of B, we use the unit vector, so it's a 1. So cosine of beta turns out to be 2 over radical 14. That gives us a beta of about 58 degrees. And then you can calculate gamma exactly the same way, right? We let the b vector be the k vector, 0, 0, 1. So a dot b is 0, 0, 3. Magnitude of A is radical 14. Magnitude of B, again, a unit vector, it's a 1. Cosine gamma. And this turns out to be about 37 degrees. So that tells me that if I want to rotate that vector so that it would point in the x direction, I need to rotate about 75 degrees this way, and then it'll be in the same direction as the x-axis. Rotate about 58 to point in the y direction, rotate about 37 to point in the z direction. Questions? Yeah. Okay. Oh, that's right. We're talking about this, right? We're missing a piece here. What are we missing here? How do we fix it? Right. So that was my mistake. Sorry about that. What I meant to say there was that cosine of theta is 1 or minus 1. So therefore, A dot B is magnitude of A, magnitude of B, 1, or length A, length B, minus 1. Right? Thanks for pointing that out. That was my mistake. Sorry about that. Okay, are we okay with this alpha, beta, gamma stuff? Yep. These three cosine things, cosine alpha, cosine beta, cosine gamma, these things are called direction cosines. In many applications, you'll be dealing with direction cosines a lot. And alpha, beta, gamma are called direction angles. So the cosine of alpha, beta, gamma are direction cosines, and the angles themselves are called the direction angles. The dot product is also very useful when it comes to calculating the projection of a vector. So here's my B vector, and here's my A vector. If you think in terms of shadow. If the sun is directly overhead, then the shadow cast by the vector B onto A will look like this. Right? That red vector is the shadow that will be cast by the vector B onto A. So this red vector, we call this the vector projection of B onto A. It helps to think in terms of shadow, like I said, the shadow cast by B onto A. And we write it this way. You write the word, the four letters P-R-O-J for projection, and then B here, and then A, vector A, as a subscript of the four letters P-R-O-J. So whenever you see this, we're dealing with the projection of B onto A. A is in the subscript, so it's lower, so it helps you remember it is something that's it's this picture here. The vector projection is obviously a vector. We'll come back to the vector projection in a little bit. It turns out that it's easier to find the magnitude of that projection first, and then we'll come back to the actual vector. The magnitude, the length of that vector is written as COMP for component of B onto A. Technically, it's called a component of B along A. It is also called a scalar projection. So it's very, very important to be familiar with the symbols we're using here. The projection means a vector projection. The outcome is a vector. The component is a scalar projection. The outcome is a scalar, a number. We're talking about a magnitude, right? So that's a number. And like I said, it's easier to find the component one first. So we'll do that next. Let's take the triangle formed by the component, the vector projection, and the vector B over here. So I chopped off the excess part of the vector A in this triangle. And let's just deal with the magnitude for now. We end up getting a right-angled triangle. The magnitude of the hypotenuse is the magnitude of B, right? And the magnitude of the vector projection is the scalar projection, or the component of B along A. The angle between them is theta. Looking at this figure here, using basic trigonometry, we can say that cosine of theta is the adjacent over hypotenuse. So it's COMP, component B over onto A over the magnitude of B. Or simply the magnitude of B times cosine of theta. Okay, so that's one way to calculate the scalar projection. But often we don't have theta. Often we know what A and B look like, but we don't have theta directly. So we want to modify this formula a little bit so we don't have to calculate theta necessarily. We can just use the vectors A and B. Here's the original picture. We know this formula, the basic dot product. If I divide both sides by magnitude of A and magnitude of B, then notice I can rewrite cosine as A dot B over length of A, length of B. And now I can replace the cosine of theta in that formula here. So if I know what A and B look like, I can directly calculate the projection without having to calculate theta first. So let's take this into here. So theta is gone. I don't need to calculate it anymore. If I know what A looks like, if I know what B looks like, I just have to do that. In fact, we really don't need this. They cancel out. So that formula in the red box is the most convenient way to calculate the scalar projection, the length of the shadow that B would cast onto A. You only simply dot them and then divide it by the magnitude of the base shadow. You don't have to calculate theta, but if you know theta, then you could use that formula. You have two choices depending on what information you have, theta or the two vectors. Make sense? Yep. Okay, now we tackle the problem of the vector projection. The scalar projection is this guy right here. Now we want to find out what is the vector projection. This tells us how long it is. And now we need to know what direction it is pointing. And that question, the answer is obvious. It's pointing in the A direction, right? The vector projection is equal to a vector this long So how do I give it the same direction as A? The unit vector. Why do we use the unit vector? Right, and we don't change the length. Excellent. So we have a direction, a magnitude here. We have to give it a direction. Direction is not just A, though. We have to put it in a unit. Find a unit vector in the same direction as A. If I don't have this part here, then A has its own magnitude. That's going to get multiplied to here and change the length of the projection vector. So if we use a unit vector, then we preserve the length, which is what we want, and we simply give it a direction on top of it. You can clean up this formula a little bit. I can put these two together down here as the length of A squared, and then multiplied by the vector A. We saw earlier that if you dot a vector with itself, you get a magnitude squared. So this could also be written as A dot A. So this gives you a couple ways to find the vector projection. All right, any question on this? Yeah. You want to do it afterwards because this stuff, right, the reason I separated them is because this gives me a number, and that's a vector. So I calculate all of the numbers together. So this could be like a 2 or something. And then I just simply multiply that to A. So we don't want to deal with this thing here first. Let's get all the numbers together and then deal with the direction. It's for simplicity. Other questions? Right. This whole thing right here, this is a scalar. Scalar. A dot B is a number, and this, of course, is a scalar. Right? Same thing here. A dot B is a scalar. A dot A is also a scalar. We're simply separating out the number part and then a vector part. Let's try this on the two vectors we had earlier, A and B. And you'll see how that works out. Right? So looking for the two projections, the scalar projection, that's just how long the projection is. And then the vector projection, that's the length of that plus a direction. If you can find that, the second part is relatively easy to do. All right, the component of B along A we saw earlier is A dot B over magnitude of A. So let's see, we get 4 plus 10 plus 18. And that's the 22? 32? Thank you. And the length of A, we had that earlier, didn't we? Radical 14? Yes. Yeah. Okay, so that's how long it is. It's a scalar, right? Right now it has no direction whatsoever. And now we give it a direction. We could use the formula we had on the last page, A dot B over magnitude of A squared times A, or we can try to make sense of this and say it's simply a vector this long in the same direction as A. And you always give the direction by giving a unit vector. Okay? Right? It's a vector this long in that direction. And so what do we have here? 32. This is another radical 14. So that's just 14, right? Times A. So what would we get? We get 16 over 7, 1, 2, 3, or 16 over 7, 32 over 7, and 48 over 7. Okay, now do you see how the scalars and the vectors are pulled apart when we do stuff like that? Yeah, we lump all these numbers and then tack on a direction. We don't usually want to mix scalars and vectors together. That can get us in trouble. But collecting them and then putting them together is a much better thing to do. One application of the dot product, if you take physics, you'll see this, is work. And this is what happens when you move an object along some direction, D, so that's where you want to move it to. with a force, capital F vector, that's not necessarily along D. So let me draw a picture here. This is the ground. And you got a box sitting on the ground. And you're trying to move this box, but you're not moving this in a very efficient way. You're using a force that actually goes like that. And then what's going to happen here, let's assume the box is very heavy and the box stays on the ground, so it goes in this direction. So it stays on the ground, but you're kind of pulling it up and forward at the same time. If you think about moving things, then the amount of force you use to pull this thing up is kind of wasted. It's not helping this thing moving along the direction, along the ground. And that's what we're calculating when we say work, right? The force that's actually in line with D, that's used to move it in the same direction. And you can find that by taking the dot product of the two. The dot product gives you some kind of projection, as you saw earlier. So by taking this is work. You take the force, and then you dot it with the direction you want it to go. And that will end up giving you the work. Okay, so if you go into physics or engineering, you'll probably see work in some shape or form. Okay, that's it. Yes?
If you had multiple forces like gravity and pushing and like downhill, would you put them together first, or would you use dot product?
I would combine the forces first and then dot it. All right, that's it for today. Have a nice weekend. See you Monday.